Chapter 6, Chemical Equilibrium. Section 6.4, Equilibria that involve solutions. When a solution is involved in a chemical reaction or physical change, the Gibbs energy of formation of the solute depends on its concentration. The standard state of the solute is often defined to be either 1 molar or 1 molo. 1 molar is denoted by uppercase M. 1 molo is denoted by lowercase m. 1 molar is 1 mole solute per liter solution. 1 molo is 1 mole solute per kilogram solvent. It's often more convenient to use a molar, 1 molar, as the standard state for the solute in an aqueous solution, just because it's convenient to measure exactly 1 liter aqueous solution using a volumetric flask. However, this 1 molar may not be very accurate if the temperature changes. Usually the volume increases as the temperature increases, the volume decreases as volume decreases. So even if you prepared 1 molar solution, aqueous solution at room temperature, when the temperature goes up, now the volume increases, the concentration decreases in molar. If you have a lower temperature than room temperature, again you have less volume, and then theoretically you'll have a lower concentration in molar. So this is more convenient to use molo instead, because 1 molo is 1 mole solute per kilogram solvent, and the mass of solvent does not change with temperature. Alright, so it's convenient to use molar, it's more accurate to use molo, especially when solvents other than water are used, and then we often just use molo as the standard state for the solute. This is just because in an aqueous solution, usually if you have 1 liter such solution, the mass of water is roughly 1 kilogram. You cannot say that for pretty much any other solvents. That's why it's often for us to use 1 molo as the standard state for the solute. 2 reasons. One, a molo is more accurate because it does not depend on temperature, and number 2, if you have a solvent other than water, 1 liter such solution may not contain roughly 1 kilogram solvent. Now let's look at a typical chemical reaction that takes place in water. So from A to 2B, A is a solute, B is also a solute in an aqueous solution. That's why you have this AQ in parentheses here and here. Now the Gibbs energy of formation of A and B depend on their concentrations, C sub A and C sub B. Right now I'm using molar. And now let's look at this equation. So we have this equation to use when we need to know the Gibbs energy of formation for a certain concentration. So this number is usually provided, the value of the standard Gibbs energy of formation of A in an aqueous solution is usually provided to you. And then what if I ask you, what if the concentration of A is not 1 molar, it's 2 molar? And then we can just take the difference between these two. This is RT times the natural logarithm of 2 molar over 1 molar. So what if it's 0.1 molar? You just need to plug in this value. And this equation will give you the Gibbs energy of formation of A with non-standard concentration, and same for B. These 2 equations are exactly the same. You just need to replace every single A with B. Now let's look at the Gibbs energy of reaction. It's 2 times the Gibbs energy of formation of B minus the Gibbs energy of formation of A. So the 2 comes from here. And then we can divide this into 2 components. This B is here, the standard Gibbs energy of formation of B and its correction. Also, we can just divide this into 2 parts. The standard Gibbs energy of A plus the correction based on the actual concentration. And then we combine this standard Gibbs energy of formation of B and that of A. We have this 2 here. And we combine the RT times the logarithm over here. So if we look at this 2, This is just the product minus reactant in the standard state. That's the standard Gibbs energy of reaction. And over here we just combine the RT and the logarithm, and we have a reaction quotient of concentrations. The reaction quotient of concentrations is unitless, again, because if you look at the expression, it's Cb over C naught to the power of 2 from here, divided by Ca over C naught to the power of 1, because the coefficient in front of A is 1, so we have this equation for the reaction quotient of concentrations. Note that Q sub C has to be unitless. Again, it's just on top, it's the concentration of B relative to C naught, and then to the power of 2, of course, and then on the bottom it's the concentration of A relative to 1 molar to the power of 1. So on top it's unitless, on the bottom it's also unitless. Now let's look at this equation again, so we can somehow compute the Gibbs energy of reaction given the standard Gibbs energy of reaction plus the value of Q sub C. And Q sub C is the reaction quotient of concentrations. If we are given the values of the concentrations of A and B, we'll be able to calculate Q sub C. When the reaction reaches chemical equilibrium, this K sub C is equal to Q sub C at equilibrium. Alright, and K sub C is so-called equilibrium constant of concentrations. Again, if we use 1 molar as the standard state for this reaction in aqueous solution, we have this equation. The Gibbs energy of reaction is the standard Gibbs energy of reaction plus RT times the natural logarithm of Q sub C. Q sub C is the reaction quotient of concentrations. Q sub C is unitless because whenever you have a concentration in an aqueous solution, it has a unit. In this case, the unit is molar, but you need to divide that concentration by C naught, which is 1 molar. That's why there's no unit in Q sub C. At equilibrium, delta G of R is 0. That means the standard Gibbs energy of reaction is 0. The Gibbs energy on the left hand side equals the Gibbs energy on the right hand side. And in this case, K sub C is equal to Q sub C at equilibrium. And therefore we have 0. This becomes 0. And we copy this here, the standard Gibbs energy of reaction plus RT times the natural logarithm. Okay, again, K sub C, the equilibrium constant of concentrations, is simply the reaction quotient of concentrations when the reaction is at equilibrium. So we have this equation, and now we have standard Gibbs energy of reaction is equal to negative RT times the natural logarithm of equilibrium constant of concentrations. Here's one numerical example 6.4.1. Let's calculate the standard Gibbs energy of reaction for this reaction. We have two reactants, H plus and OH minus, in the aqueous solution. There's only one product, water, in the reaction system. The reaction proceeds at room temperature, and we have the equilibrium concentrations of H plus and OH minus. They are both 10 to the power of negative 7 molar. So K sub C is, again, products always on top, reactants on the bottom. And you can see I was dividing those concentrations by 1 molar. It's just because on the bottom we need to have the relative concentration. We use 1 molar as the standard state. So the relative concentration over here is 10 to the power of negative 7 molar over 1 molar. So we have this. Water is a pure liquid. Whenever you have a pure liquid or pure solid, the standard state is its mole fraction, and the mole fraction of a pure liquid or solid is simply 1. So that's why I put 1 on top, and then we do the numerical calculation. We have 10 to the power of 14, and then we can compute the standard Gibbs energy of reaction. It's negative RT times the natural logarithm of K sub C. We plug in this number, we plug in R and temperature T, 298. We get negative 79.9 kilojoule per mole. Alright, to verify these results, we can use the values of the standard Gibbs energy of formation for H plus, OH minus, and water. We have those numbers here. Actually, the standard Gibbs energy of formation of H plus in water is just defined to be 0. It serves as a 0 reference. And then OH minus is this, and water is this. So we can do the calculation. We can have water minus H plus minus OH minus. So we have this setup over here, we get negative 79.9 kilojoule per mole. So given the standard Gibbs energy of formation for all chemical species in the reaction, we can calculate the standard Gibbs energy of formation. Given this K sub C, the equilibrium constant, we can also compute the standard Gibbs energy of reaction. And these two different calculations result in the same value, negative 79.9 kilojoule per mole for this reaction. Therefore, we are confident our calculation was correct.